So an equilibrium constant is part of what's happening. It describes how far the chemical reaction will go. We've got reactants and products, and which is there going to be more of, how far is it going to go. But it doesn't tell us anything about how fast it's going to get to that point. So reaction rate is what tells us how fast it's going to get there. We mentioned this earlier in this chapter, but there's a barrier to reactions, and we call it the activation energy. We talked about this with collision theory, that when the molecules collide, they have to have enough energy to react. If they're moving too slowly and collide with too little energy, nothing happens. They got together, but there was no, it's like two people meeting and you're both just, tired and out of sorts, and you're like, eh. Whereas if you had met when you were, feeling rested and happy and had a lot of energy, there may have been sparks and you may have been interested in this person. So that activation energy is a barrier that has to be overcome in order for the reaction to occur, for the reactants to be converted into products. And usually that activation energy has to do with the original chemical bonds needing to be broken before you can make new ones. So here's an example of hydrogen and oxygen gas. So you could have a balloon, I need to switch over here. You could have a balloon full of hydrogen gas and oxygen gas. And we did this in a demonstration that we did in college. Balloon full of hydrogen and oxygen. And it's just sitting there, it's not exploding or anything. There's no reaction occurring. They're just coexisting, la la la. Then you take a candle on a stick, a little spark on the candle. Kaboom! Big lecture hall, the ceiling tiles jump up. We're like, we made that one a little too big. Very, very explosive. Why didn't it react before? The activation energy wasn't overcome. You need something to get it going, to break the initial bonds, and then, if it's an exothermic reaction, it provides the energy to break more bonds. So you have reactants, they have a certain energy level, potential energy, they have a certain energy level, but we need to get up and over this hump. We need enough energy to break these bonds so that we can form new ones. If we get up over the hump, then it goes really fast. Lots of energy is released, and we end up with products that have lower energy than the initial reactants did. Things are always going to go to a lower energy state. So if the reactants are higher in energy and the products are lower, the reaction will proceed in the forward direction. But if there's an activation energy, you have to get over that hump. If you don't have enough energy to get over the hump, nothing happens, and they just sit there. It's a little bit like playing miniature golf, where you hit the ball and you didn't hit it hard enough to go over the hump. So you don't get to the other side. You have to hit it harder. And once it goes up and goes over the top, then it goes fast down the other side. Does that make sense? So the activation energy is this hump, this barrier that we have to overcome. And this is where the slides get kind of busy. So is there any way to speed up a slow reaction? Yeah, there is. So the balloon with the hydrogen and the oxygen in it, and you sit there all day and look at it. Nothing's happening. That's a really slow reaction. Other reactions will proceed, but they'll proceed very, very slowly. Is there a way to make them go faster? Yeah, there's several ways. So the higher the activation energy, the fewer the number of reactant molecules that are going to make it over that barrier, and the slower the reaction rate. So that makes sense. If the hump is really tall, you're not going to have many particles that can go over. Why would any particles go over? Well, all the particles in a substance do not have the same energy. Okay, just like all the people in a room don't have the same energy, right? They don't all have the same grades or the same amount of money or anything, but there's an average. And so you have this random molecule that's got a lot of energy. If that happens to run into another random molecule that has a lot of energy, they might together have enough energy to get over the hump, and they will react. And so you'll have just a little bit of reaction occurring, but not so much that you would necessarily even notice. And the taller that hump is, the fewer that are going to get over it. So in general, at a given temperature, the higher the activation energy, the slower the reaction rate. The higher the hump, the slower the rate. Well, one way we can increase the rate is to increase the concentrations of the reactants, because then you're going to have more collisions. Another way is to increase the temperature, because that increases the number of collisions, but it also increases the amount of energy that they have when they collide. So increasing the temperature will generally increase the reaction rate. Or we can use a catalyst. And catalyst is a word that we use in everyday life too. We say, well, he was a real catalyst for change in that situation. And the chemical meaning of catalyst is similar, but not exactly the same. A catalyst is something that lowers the hump, that lowers the activation energy. So here we have a picture of what are those? Boulders being pushed off a cliff. So without a catalyst, you have to push the boulder up this steep hill before it can fall off the cliff. And that requires a lot of energy, and not many of them are going to get up over that hump. The catalyst provides an alternate pathway so that you can go around the hump. Okay, so now it's much easier to push these boulders off the cliff because we don't have to go up and over this wall. We can go through the gate. And it's easier to just push them along the ground and off the cliff instead of going up and over this hump. So it provides an alternate pathway. So you could push harder to increase the reaction rate, which is like increasing the temperature, or you can find a different way, an easier way. And that's what a catalyst does. Catalysts are like crazy important. So the catalyst provides an alternative pathway. So instead of having to go up and over this activation energy, now we can go this way, and the activation energy is much less. So more particles are going to have enough energy to get over that little tiny hump, and the reaction will go faster. Your body is full of reactions that are catalyzed. And that's one of the ways that your body controls which reactions occur and when and to what extent. It can do that by controlling the catalyst. A lot of reactants are thermally sensitive. So if you heat them up, heating would increase the rate, but if they're thermally sensitive and decompose when you heat them, that's not going to work because you're destroying your reactants by heating them up. And so the only way to speed those things up is to use catalysts. So most of the thousands of reactions that must occur for a living organism to remain living are too slow to occur at room temperature. They just don't happen. So our bodies use enzymes, which are biological catalysts. And the enzymes provide a lower energy pathway for those reactions to occur so that they do occur at an appreciable rate. So here's an example of the enzyme sucrase. So sucrose is a disaccharide. It's two sugars joined together. It's glucose and fructose. And your body wants to break that into the monosaccharides, glucose and fructose. Well, the activation energy at body temperature is pretty high. It's just not really going to happen. But there's an enzyme called sucrase that lowers the activation energy and allows your body to break the sucrose into glucose and fructose. I'm not going to quiz you on the details of this. It's an example. some of the genetic diseases that people have are because their body lacks certain enzymes and they cannot do these chemical processes that are needed in your body. And so, if you're, I think galactosemia, your body can't handle galactose. And so it can build up and cause all kinds of nasty damage and stuff. And so then you have to avoid consuming galactose because your body can't deal with it because it's lacking an enzyme. So how do enzymes work? They're really kind of cool. They're generally large molecules. And so what the enzyme does is it has an active site. And so the molecule of interest will fit into this active site. And what it's doing is it's causing this bond between the two monosaccharides to be weakened. Because it's like holding the one over here and the one over here. It's like, oh, let's pull you apart a little bit. Okay, now it's harder for you to hold on. Now it's easier. We broke it. Gotcha. And then it releases them, and another one comes in. And so enzymes have an active site where the molecule can fit in, and when it's in that position, it's much easier for the reaction to occur, and so it occurs much faster. And you get into things where you can block the active site, and there's all kinds of fun stuff. If you're interested in that, that would be Chem 21. And so that's the end of the chapter. Any questions about catalysts?
What's an example of a catalyst? Like, that we would
Well,
use in a lab or something?
Any of the ACEs are enzymes. Sucrase, lactase, all of those things are enzymes, and those are biological catalysts. Catalysts in other reactions can be lots of different things. Sometimes nickel or palladium, different metals can be catalysts. The thing about a catalyst, which the slides didn't really mention, that I think is kind of important, is the catalyst does not get used up. The catalyst just goes over and over and over again. So the analogy I like is kindergartners going over a fence. Okay, so you've got this big fence, just like not a barbed wire fence or anything, but just, here, I'll draw a picture. Children escaping from the playground.
There's a barbed wire fence.
No. Okay, so this is what I'm talking about. So here you've just got this, standard classic farm fence, right? And we've got all these little kindergartners over here, and for whatever reason, they need to get to the other side of the fence. Okay, so when Andrew's there, he's going to be one of those high-energy kids that he'll just go over the fence, no problem. But other kids are slow, and, it's going to take a while if you wait for all the kindergartners to climb over the fence. Well, what if you have a grown-up here picking the children up and putting them over the fence? That's going to speed things up, isn't it? A catalyst, yeah. So the grown-up, to put this down, the grown-up picks up the child and sticks him over the fence, much faster than waiting for the kid to climb up and over. Is the grown-up done? No, he's done with that kid, and he picks up another one. And so the catalyst does not get used up. When you're done, the catalyst is still there, could be reused. It's not consumed in the reaction. It doesn't come into the stoichiometry of the reaction or anything. All it does is it increases the rate. It does not affect the position of the equilibrium. It just allows the reaction to get to equilibrium faster. So instead of maybe taking days, it'll take minutes or seconds instead of hours or something like that.
Are different catalysts different? Like as far as how much they affect the reaction, different catalysts are like better or worse catalysts, or all the same?
They'll affect it in all kinds of different ways.
Okay.
And what is a catalyst for one reaction may do nothing for another reaction. And a catalyst that works great under one set of conditions, under a different set of conditions, pressure, concentration, or something might not work. And so it's a very individual thing.
Haven't they figured out how to engineer catalysts to do things that normally you can't do?
Yeah, that's one of the things people do. It's like, okay, we want this reaction to occur and it's not occurring. How can we get it to work? And so they look at things like Vesper theory and the shape of molecules, and so they don't just blindly try stuff, but they understand the reaction as much as they can, and then they look at, well, what could we do to facilitate this reaction? What's really just crazy about living organisms is all these very complicated enzymes. And, you just get one little mistake when the enzyme's made and it doesn't work anymore. And then your body has things that it'll send out to block the enzyme. It's like, maybe you're metabolizing the sucrose, and it says, no, we don't need you to do that anymore. And so it'll secrete something that can block the enzyme. And then later it'll say, okay, we need to turn on again. And so your body uses that like little switches to turn processes on and off. And the more you study the chemistry, it's called biochemistry or biological chemistry, the more you study that, the more just like, wow, crazy that our bodies work at all. So anyway, these are the slides showing chapter and review. And I'll get the homework posted today for you. And I know, big cheer, right? Yay!